So now here I explain what is random variable. Random variable is a variable that takes a string like this, getting 0 heads, getting 1 head. Experiments outcome we wanted to predict. Right? So we wanted to see how the experiment's behavior is to actually hold that whatever experiment or the outcome we are trying to predict, there should be some variable x or y or whatever, but that will hold this kind of a thing, getting 0 heads, getting 1 head, getting 5 heads, like that. Okay, and when you can count the outcomes, it is called as discrete random variable. Right here I can say 0 heads, 1 head, 2 head, 5 heads, because 5 times I am throwing. Okay, but in a continuous random variable you cannot actually exactly say getting 1295 as the stock price today, because it's a real number and it can oscillate between, or it can range between, it can be between a range. So continuous random variable generally is predicted between a range. Okay, and discrete random variable generally we take it in as a unique number like this, getting 5 heads, like that. So we need to understand theoretical distributions, because in real time when you look at data, it will have some kind of a distribution. If you know some theoretical distribution, some basis, then you'll be able to make some understandings out of the data. So to make some understandings or bring out some insights from data, we are actually trying to understand some theoretical distributions. I took examples of Gandhi, Nelson Mandela, or some political leader. When you are trying to describe about one person, one political leader in current era, you may take a person who is already was there, right? So that's a theoretical distribution. This is the current practical data. So to make the inference very clear, we need some theoretical distributions. So theoretical distributions will have their behaviors and we'll use them. In normal distribution, we have seen that, the 95%, 68%, 95%, and 98% rule, right? That 3 sigma rule, right? So like that we'll have behavior. So to find out probability distributions, probability density, we have formula for binomial distribution. When the experiment, when the experiment's outcomes are only true or false, then we call it as Bernoulli trial, and we call the distribution as binomial distribution. If you have the experiment's outcome more than 2, you call it as multinomial distribution. For multinomial and binomial, we'll use the same formula. Okay, probability density function. What is probability density function? The density of the height of the bar, right? Height of the bar is the density. The function which actually predicts or finds out this height is the probability density function. Right? The count and the probability are same, I said, right? When you look at when you look at throwing coin 5 times, total outcomes are 32. Getting 1 head is only 1. Getting all heads is only 1, because now all heads will happen only once out of these 32 occurrences. So it's 1 by 32. And when you use the formula also, you are getting the same value. Getting 1 head, 5 by 32. When you use formula also, you are getting the same thing, right? So when you try to do a plot, it is going to be like this, getting 0 heads, getting 1 head, getting 2 heads, getting 3 heads. It's going to be like this. It is binomially distributed. Theoretically, it is binomially distributed. Okay. Even if you take out the denominator out, ignore the denominator also, shape will not change. That means count and probabilities are kind of equal, kind of synonyms. In a in a complex setup, probability is going to be more than counts. But in this particular scenario, when you are trying to understand distributions, the count and probability are synonyms. So when you know counts of each of these, random variables occurrence, you can actually do the plot, or you can actually assess how the data is behaving, right? So probability and count are kind of synonyms we can use. Okay, and this formula, the probability density function, is derived by doing many experiments there. Here, if you look at this bar graph, the bars are, bar widths are very high, very big, right? If you do a million times, if you do the same experiment million times, throw a coin million times, and trying to calculate what is the probability of x is equal to 0, the bar is going to be like a line, right? Do you agree? If you do this experiment for million times, the bar is going to be like a line, right? Then you will get many lines, and then all those lines combined, you will get a curve like this. Okay, so a binomial distribution reaches normal distribution when the number of experiments are too many. Okay, that's a theoretical point. Binomial distribution reaches normal distribution when the number of experiments are too many. Did you get this point? Any questions there? Okay. So when the experiments are too many, binomial distribution reaches normal distribution. At that point in time, whether you use this formula to find out density or this formula to find out density, doesn't matter. Okay. Probability mass function and probability density function are same. Probability mass function is for discrete random variable, and probability density function is used for normal distribution. Okay, so mass function is like if you look at this, out of 32 occurrences, one occurrence is all heads, right? 1 by 32. This is mass, probability mass function. This is like count of favorable events divided by total number of events is the mass function. Okay, and then normal distribution when the random variable is continuous. Where random variable continuous means the stock price, right? It's a continuous random variable. The numbers data will be between between two numbers there will be infinitely many numbers. Okay, so you cannot calculate f of x, right? A particular number's probability you can using this formula. Theoretically you cannot. Practically you can by using this formula. Theoretically you cannot, because if you look at many lines here, right, at a given x, theoretically at a given x, there will be a line. What is the area of a line? What are we trying to find by using this probability density function? Area under the curve we are trying to find. So if you take normally distributed data, the area under that curve is going to be 1. Total area under that curve is going to be 1 because they are probabilities, right? Total probability is going to be 1 for a particular random variable. The area is going to be that much. But if you have 10 numbers, for all are equally distributed, then for one number it's going to be 1 by 10, right? So like that. But here it's a normal distribution, so it's not going to be 1 by 10. There will be some numbers, right? You can calculate that probability using this probability density function. Density is the height, I said, right? Probability area, right? Height and width also, both actually, but I am trying to make it easy by saying that height. Okay, so it is the height and width, the area of the curve, area of the bar is going to be found by this formula. Generally, theoretically, when they say you cannot find out probability for a given point because the area of the line is going to be 0. But in real time, we will actually calculate probability for one data point also in continuous setup. One data point also. We'll see that in anomaly detection. Okay, and we will calculate area between one point and another point. If you take from here till here, that's going to be on a blue line, blue graph. From here till here, the area under the curve is going to be 1. Okay, if you take a particular part, right, from this is like minus 0.5 to 0, you need to integrate this formula from minus 0.5 to 0. Do we need to do that? No, we will not do it. Theoretically, we are trying to understand how to use this formula. When data is normally distributed, area under the curve is 1. That is one point you need to remember. And to find out probability of happening of a random variable falling between two numbers or falling within a range. To calculate probability of a random variable falling within a range, if you take the stock price, the probability of falling that stock price falling between 1235 and 1240 can be calculated by integrating this between those two numbers. Integrate 1235 and 1240 and then use this formula. Okay. So the area under the curve is 1 of a normally distributed data, and you can calculate probability of any range when the data is normally distributed or close to normally distributed, because you have this probability density function which will be useful for calculating the probability or predicting the value, right? Predicting how much how much probability is there to happen that particular thing. So when the data is normally distributed, 3 sigma rule we call it as, within one standard deviation there is going to be 68% of the data. Within 2 standard deviations there is going to be 95% of the data. Within 3 standard deviations it's going to be 99.7% of the data. Within 100% of the 100% is going to be like 3 standard a little above 3 standard deviations. We are not saying 100% because these lines will never meet the x-axis. Right? This curve will never meet x-axis. If you look at the formula, you can understand that. If you take x, right? So x is going to be some different. X is equal to mu. What happens? This is 0, right? E power 0 is 1. 1 by sigma into whatever this, right? This is going to be a number which is not equal to 0, but a big number, right? If x is very far from mu, right? If you substitute this, it's going to be big number. This is going to be big number. E power minus big number is going to be 1 by e power whatever, right? E is 2.37 whatever, right? So 1 divided by a big number is not going to be 0, but close to 0. Are you getting it? X is far from mu. What happens? What is the probability? What is the density of that? In a normally distributed data set, if x is far from 0, what happens to this formula? What is the value of this formula? Can you calculate? Suppose that mu is 7 and x is 1 million. What happens to this total formula? Anybody can anybody tell me? If x is 1 million and mu is 7 or maybe 10, what happens to that total formula? Can anybody? Guys, please. Did you get my question? Did you guys get my question? Yes, no? Should I repeat or should I explain?
Explain that one more time.
Yeah.
I think we are confusing.
So yeah, so the point here is I made a point, right? I made a point. The point I made was when data is normally distributed, the curve is going to always be like that, bell curve. And these lines, right? These lines will never touch x-axis. These lines will never touch x-axis. What that means? For any given value, right? The y value is not going to be 0. Y, what is y? F of x is the y. Right? This is y, right? This x is the are the values here. So if you look at the example here, if you look at this example, salaries are the X. Okay, salaries are the X, and number of count I have taken as Y, but you can take probability also. Total 32. Count divided by 32 is also going to be probability. Okay, so for any given X, the Y is not going to be, the probability is not going to be 0. That's the point I was actually making. So especially when data is normally distributed, it is not going to happen. Give me 1 second. So I said that it will not touch, right? Theoretically also it is true. If you look at this formula, suppose that mu is 10. Suppose that mu is 10, mean is 10. So for some data set, right, which is normally distributed, the mu is 10 and X is 1 million. Is that possible? X can be any value, right? X can be any value. X is like, the salary or whatever, right?
Yes.
So the data can be like that. So if I substitute that into this formula, what happens? 1 by sigma square root of 2 pi e power minus 1 by 2. This is a big number. Minus 10 is going to be big number, maybe around 1 million divided by sigma, right? Sigma maybe 10 or 20, maybe 100. Even if you take 100, it's going to be 10,000, like e power 10,000. A big number will be there, right? Here, right? Here it's a big number. So
Yes.
e power a big number is going to be negative big number is going to be 1 by sigma square root of 2 pi into a big number, right? 1 divided by big number, 1 by 100 is 0.01. 1 by 1000 is 0.001. 1 by 10,000 is 0.0001, right? Like that it is. It's going to be around this number, right? So it's going to be around that, approximately 0.0001, right? So any number you take, you calculate probability density or the probability of that number, it is not going to be 0. That means Y is never 0. That's where it will never touch the x-axis. That's where, within 3 standard deviations, they are saying 99.3%. Right? Within 3 standard deviations, 99.7%, sorry. Right? There is always possibility that some data points will fall beyond the 3 standard deviations, even when the data is perfectly normally distributed. If you look at this example, right, you should understand. Right, I have taken 32 employee salaries and then I tried to plot them. When I plotted them, I've got a bell curve. And that means data is normally distributed. When data is normally distributed, what we are saying, 68% of the data should be within 1 standard deviation. What is data here? The salaries of the employees. So 68% of the employee salaries should be within 1 standard deviation. I calculated mean and standard deviation. Try to see whether it is happening or not. 37,596 and 71,867 are the numbers, right? And then 68% is going to be, right, on the, we have done a code example also. I'll show that today, tomorrow. Right? Theoretically, we will learn this today, but I'll show you a little bit here. I'll show you this one again tomorrow. Okay. Maybe for 10-15 minutes only. Whatever graphs we have seen there on the slides, right? I just implemented it here. So this is the graph we saw. how to do these graphs also. So this is normally distributed data, and then mean and standard deviation I calculated. 68% of 32 is going to be 21.76. Around 21 people. Okay, 21 people should fall within one standard deviation. What is within one standard deviation? 37,596 and 71,000. 37,000 and 71,000 salaries. 31,000 and 37,000 and 71,000. So I try to filter the data, filter the people, number of people between these salaries, right? Salary greater than 37,000 and less than 71,000. When I looked at the count, 20 people have came there. See that when data is normally distributed, see around 68% of the data is within one standard deviation. What is data here? Salaries. Did you get it? I'm actually trying to compare theory with our practical example. I took some simple example and trying to show you that. Any questions?
No, Rama.
Okay. So 95% of the data is going to be within two standard deviations. What is two standard deviations? No, salary mean plus 2 into standard deviation and mean minus 2 into standard deviation. Right? Mean plus 2 into 2 standard deviation and minus 2 standard deviation. What are those values? See this mean, right? Mean is this number. Minus 2 standard deviations is this number. Mean plus 2 standard deviations is this number. So 95% of the 32 is how much? 30 people. Around 30 people should fall. 30 people's salary should fall between 20,000 and 89,000. Let us see. I filtered again the data and tried to look at it. See this 30 people have fallen. 99.7% of the people are going to be within 3 standard deviations. When I calculated 3 standard deviations, right, it actually went beyond. So this will happen. How good the data is normally distributed. Again, when the data set size is small, it will always tend to, these, the 3 standard deviations thing is going to, like, it actually went off, right? 20,000 and why I kept 20,000 here? This is wrong number, I think, right? So I calculated something here and kept it. That's the wrong number. Sigma plus 3 standard deviations is not 20,000. See this 1 lakh whatever, and sigma minus 3 standard deviation 3,000 it is. So I kept these wrong numbers here. Okay, I need to update that. That in the file we have it at 3,000 and then 1 lakh, but the data is not there in that range, right? So beyond 20,000 we don't have data there because the data set is small. It is actually happening like this. If the data set is too big, right, then the 3 sigma rule will exactly match. 3 sigma rule will exactly match. So normally distributed normal distributions are symmetric around their mean. What is symmetric around their mean? If you look at the mean and the data around it, see that it's like the number of data points are falling, reducing when you go below it. Number of data points are falling above it also, right? It is symmetric, right? Either way, whichever direction you take, the number of data points will reduce. Number of data points will reduce means probability will reduce for that particular salary. Got it? And then mean median mode of a normally distributed data is going to be same, and area under curve is going to be 1. Normal distributions are denser in the center and less denser in the tails. What are tails? These are called as tails. Right? These edges are called as tails, and this is center. Okay. So we'll talk about left tail, right tail distribution. The skewed and kurtosis and all that tomorrow. Normal distributions are defined by 2 parameters: mean and standard deviation. So mean and standard deviations are key to understand normal distribution. Why did we understood this? Whenever you plot a graph and it is forming a bell curve, immediately you can understand that 68% of the data is very close to mean and 95% of the data is going to be uh, kind of within two standard deviations. Right? When I say two standard deviations, one standard deviation, it is z-score. Right? Z-score of this number is going to be 1, z minus 1. Z-score of this number is going to be plus 1. Z-score of this number is going to be minus 2. Z-score of this number is going to be plus 2. I need to change these numbers. 3000. Z-score of the 3000 is going to be minus 1. Z-score of this plus 3000 is going to be plus 3 sigma is going to be plus 3. Okay, so we understood z-score, sigma, so standard deviation and mean, and they are very important in understanding normal distribution, and normal distribution is very important for AI career. Okay, so you try to understand this, come up with questions tomorrow. Tomorrow also I'll take maybe 15-20 minutes on this. This is very important. That's where I'm taking this much time. Rather, I'll not take this much time. Okay, so any questions for me?
Yeah, Rama, what is exactly like a G-score formula?
G-score formula is x minus mu by sigma. X minus mu by sigma, right? X minus
So,
mu by sigma.
I remember that earlier you said that like x minus mean by standard deviation, right?
Yeah, that's the mu is mean
Yeah,
and sigma is standard deviation.
here mean minus, for example, mean minus 2 into standard deviation, right?
Yeah, that's the point, right? You are actually thinking now. Very good, right? We are actually calculating a number which is at first z score 1, a number that has one z score 1. This number has got z score 1. This number is from data. This is salary.
Yes.
This is salary. This salary has got z score 1. When you try to calculate z score for this one, right? Well, how do you calculate? This is the data point. This is x. Okay, minus mu divided by sigma will give you
Okay,
1.
okay, that is x. Okay.
Right? This is x. This is x
Uh,
at 1 z score, minus 1 z score. This is x at plus 1 z score. This is x at minus 2 z score. This is x at plus 2 z score. 3000 I have to put, and then 1 lakh I have to put here. 3000. I don't know whether I have that PDF PPT available. Let me see. I'll change it. So those are the data points at that z score. Okay, the data points they are, right? Two standard deviations away. That means a data point we are talking about. A z-score of two standard deviations is like no, in terms of standard deviation we are talking.
okay, got it.
All PDFs are there. Where? I don't know. Right? Maybe I'll have it here. So any other questions? Data distributions. What is that number? 3000. 3316 here. 3316. One, 1061. Are you getting it? Anyway, I'll cover tomorrow also. So,
Yes, Rama, I got it.
okay. So these are the salaries at that Z score. So you should get the clarity also. What is Z score and what is data point also you should get by looking at this particular example. Okay.
Yeah.
So shall I stop sharing and hand it over to you guys? You guys in the sense, if you have done something, you can share it with Bala and Keshava and get clarification. And if you want to, if Bala wants to explain something, you want to listen, that's also good. I stop sharing. Anybody did anything they want to share and ask questions about? Mahesh, I think you had some difficulties. They were all resolved, right? They got resolved, right?
Yes. Yes.
So
But
any practice did done, any questions in there? No. So I'll go on mute. Bala and Keshwa, you take over and try to
Sure, sir. Sure, sir.
show some light. Any questions on the topics? Like even if you don't understand anything, also you should ask uh, Bala. Look, it's a different perspective, right? The way they are going to explain is going to be a little different. So you may understand. That's the thing.
Sure, sir. Stop recording, sir.